Uh, Very good afternoon to all of you. Welcome back to the series of lecture or discussion on the heat exchanger. So let's today continue our discussion over the problem practice of heat exchanger. So let us read it out. The first, what is the problem given? The problem says that water is heated in a building from 20 degrees centigrade at a rate of 84 kg per minute by using inlet hot water at 110 degrees centigrade in a single pass counterflow heat exchanger. Find the heat transfer if hot water each flow each 110 kg per minute. Calculate the exit temperatures of both the streams. The overall the overall heat transfer coefficient is 320 watt per meter square per Kelvin and the heat transfer area is 20 meter square. The specific heat of water is given as 4.18 kilojoule per kg per Kelvin. So this is the problem. Now we are all aware that we should follow the standard procedure, that you should write down that in the 2 or 3 lines you should have mentioned what the problem says exactly. Thereafter you should you should write down what is to find out, thereafter the schematic diagram, and again the assumptions, and at last the analysis part. So let's jump directly to the analysis part. So in these cases, see here, the water inlet temperature is given, hot water inlet temperature is given, and no other two temperatures are mentioned. It is being asked what are the heat transfer as well as the exit temperature of both fluid is being asked. So this problem will be solved, can be solved by the use of effectiveness and NTU method. So what are the steps in the NTU effectiveness method? The first step to identify the minimum fluid. So in the same process, since mass flow rate of cold fluid as well as mass flow rate of hot fluid is knowing, also their respective specific heat rate is given, so we can determine the heat capacity rate for cold fluid as well as for the hot fluid. So the cold fluid, the heat specific rate is defined as the mass flow rate for the cold fluid into multiplied by the Cc, the specific heat. So it is given as a 84 kg per minute. So we need to convert it into kg per second. So it will become 84 kg per 60 second into 4180 joule per kg Kelvin. So final we will get the value as 5852 watt per Kelvin. Again, for the hot fluid, which is also a water, we can determine the heat capacity rate in a similar fashion by the multiplying mass flow rate and specific heat. So again, we need to convert, we need to give attention upon the unit also. So we have calculated as 7524 watt per Kelvin. So out of these two, we need to identify which specific rate is minimum. That will be called as minimum fluid. So specific rate for the minimum will be minimum out of these two. So we have identified as hot fluid is the minimum fluid, which specific rate is. Okay, so actually this is the wrong, that C minimum will be 5852. So please correct it. Wrongly we have written here. So 5852 should be the minimum fluid. That means the cold fluid is the minimum fluid and hot fluid will be the maximum fluid. So the ratio we can determine C minimum upon C maximum as 5852 divided by 7524 is equal to nothing but 0.778. This mistake will have no impact further on the problem because the C minimum and C maximum ratio we have taken correctly. So the C minimum and C maximum ratio we have identified as 0.778. In the next step, first we have identified the minimum fluid, thereafter the C minimum upon C maximum, thereafter the NTU value we need to determine. The NTU value is defined as the UA upon C minimum. UA is given, area is also mentioned, C minimum we have identified, therefore we can determine NTU value as 1.094. Now we have two alternatives. We got C minimum upon C maximum and NTU. For these two, by using these two quantity, we can read out from the plot of effectiveness NTU chart. So earlier, with just in the similar fashion where we had earlier read out from the chart the value of effectiveness. So here we are calculating the effectiveness by the use of equation that we have derived for the counter flow, and we can recall it as the formula is effectiveness formula is 1 minus exponential of minus NTU into 1 minus C minimum upon C maximum divided by 1 minus C minimum upon C maximum exponential of minus NTU into 1 minus C minimum upon C maximum. So this is an expression for counter flow. In a similar fashion for parallel flow, we had derived an expression. So now in this expression, we need to know the NTU value that we have already calculated as 1.094. Also, we need to have the value of C minimum upon C maximum that we have already calculated as 0.7778. So by substituting the C minimum value and the NTU value, we can able to calculate the counter flow effectiveness value, and we have calculated it as 0.55. So this is the effectiveness value that we have calculated by the use of equation. In this also, since we have the C minimum and C maximum value and correspond NTU value, so by the use of these two quantity, we can determine the value of effectiveness from effectiveness NTU chart for the counter flow. Likewise, in the previous numericals, if we can read out, then we will get the value as a 0.52. Since out of these two, that effectiveness, the value of effectiveness is more reliable by the calculation done using equation, will be more reliable, and that will be the more accurate than that of the effectiveness value that has been read out from the effectiveness chart. So out of these two, since the equation calculation is more accurate, so we will take the effectiveness is equal to 0.55 value and continue our solution since it is more accurate. So we are taking effectiveness value as 0.55. In the next step, we will determine the Qmax value. What is the Qmax value? Qmax value is nothing but, see, effectiveness definition is Q upon Qmax. Now, what is the definition of Qmax? Qmax is the C minimum into inlet temperature of hot fluid minus outlet temperature of cold fluid. That means the C minimum into the temperature difference, inlet temperature difference of hot as well as cold fluid. So Qmax inlet and inlet temperature of hot and cold fluid is given, minimum value of specific heat rate is given. So by using the effectiveness value, we can determine the actual heat transfer rate. So Q will be equal to nothing but effectiveness is 0.55 and C minimum we have calculated as 5852, THI minus TCI is 110 minus 20, and we got the value as a 289674 watt. So this is the the first part problem where we need to calculate. See, the problem for the first part was to calculate the heat transfer. Find the heat transfer if the hot water flow is 108 kg per minute. So in this way we have calculated, we have done the calculation for the heat flow. Now we need to determine the remaining temperature. That means the outlet temperature of both stream, hot and cold stream. So how we will calculate it? So this is the, by doing the energy balance. See, what will be the energy balance? mCp delta T is equal to mCh delta T. mCp delta T for the both hot fluid as well as cold fluid. Means what? The heat given up by the hot fluid will be taken up by the cold fluid. So the Q will be equal to CH, specific heat, MHCpH into THI minus TH naught will be equal to CC, TC naught minus TCI. Now the Q value we have calculated as 289.7 kilowatt. CH we have already calculated. CC value we have already calculated. The inlet value of HI is given. TCI is also given, but TH naught and TC naught is not given, but it is our job to determine. Therefore, by using this equation, Q is equal to CH, TH minus TH naught. Q is known, CH we have knowing, THI is knowing. We could find the TH naught. In a similar fashion, Q is equal to CC into TC naught. We will be able to determine TC naught. So let's first consider this equation. So by equating this equation, we can determine TH naught is equal to how much? TH naught is equal to THI minus Q upon Cmax. So by substituting these two all the data, we can have the 110 minus, by this substitution we will be able to determine the value as a hot fluid outlet temperature as 71.5 degrees centigrade. In a similar fashion, by considering this Q is equal to CC into TC naught minus TC minus TCI, we can determine the value of TC naught. So TC naught is equal to TCI plus Q upon C minimum. So in this way, we will determine the TC naught value as a 69.4 degrees centigrade. So in these steps, what we have followed, let's recall from one to one. First of all, we had calculated we have identified the minimum fluid, that is the C minimum. Thereafter, we had calculated the NTU, that means C minimum we had identified. Thereafter, we had calculated NTU, we had calculated C minimum upon C maximum, and by the use of these two quantity, we had calculated the C effectiveness value. Thereafter, we had calculated the value of Qmax as a C minimum into THI minus TCI. Now, by the multiplication of this Qmax with epsilon, we had able to calculate the value of Q. Now, by using this Q value, we were able to calculate the TH naught value as well as TC naught value. So this is the standard problem solving procedure which today so in this way we had completed the numerical practice based on the effectiveness NTU method. I hope you have understood very well. Thank you very much.